welcome back. You know, continue this process. Hopefully, it's working out okay. Again, please email me. You have any questions? More than happy to meet up with you. We'll do a Zoom meeting if you need some help. If you need some extra resources, let me know. Just please, just reach out to me. Anything you need, let me know. All right, moving forward, we're going to start looking at charges starting to move. At this point, it's always been this charge is at this location, that charge is staying there. It's not moving. It has the potential to move. It has a certain force. And, an analogy would be you're lifting a rock or stretching a rubber band, and it has a certain amount of potential energy. Now we're going to start getting into that kinetic energy. What happens when that charge starts moving? The next couple lessons are going to try to draw analogies between gravitational energy, potential energy, kinetic energy, like we did with the roller coasters, an object falling, the pendulum, and electric fields, forces, and electric potential energy, because we already hopefully have a really good understanding of potential energy when we talk and kinetic energy when we're talking about objects moving. So to try to transition to something very abstract, we're going to try to create that analogy and that link between what we understand and this new stuff. So kind of try to draw those analogies going forward. We'll eventually get into terms that you may have heard, just may not understand what it truly is, such as voltage, current, and resistance, the three kind of main measurements when you talk about electricity. All right, so you can see here on the main learning target is draw the analogy between gravitational potential energy and electrical potential energy. Just let me draw your attention and remind yourself, when we talk about potential energy, we've always talked about it being stored energy. Okay? The units were measured in joules. And from a standpoint, when we talk about gravitational, it's always been in terms of mgh, mass times g times always been on its height. Okay. Now, we never drew field lines for gravity, but gravity field lines would always be drawn down because that's where they're always going to go. Or that's where an object's always going to go. Objects always fall. Now, if you take an object at, let's say, location A, and you take it and you go to a location B. I went in this case against the field lines. I lifted something higher. So what I do when I go against gravity's field lines, I'm going to increase its potential energy. If I take the object from location B to location A, in other words, I lower it, I'm going with the field lines. I'm decreasing its potential energy. Okay, we never talked about it in those terms, but those are the terms I want to start talking about because that's how we're going to transition to the electric field and electric stored potential energy. So we're in, think about these. We never really talked about gravitational field lines, but they're there. We just always talked about lifting an object, raising its potential energy, or lowering it, decreasing its potential energy. But we're going to think about it in terms of potential energy in these field lines. Okay. All right. So I'm going to skim through these. Some of these are, you should already have a pretty good understanding of. So here's kind of the first drawing. It's kind of what I talked about. You have an object that's high up, high potential energy. Again, it's all related on its height. If you think about these imaginary field lines, gravity's field lines are always down. And what I want you to think about, are you going with the field lines or against? Okay. In this case, when you lower it, okay, work is being done by gravity. When you lift it up, work is done by that external force. In this case, it's the person's hand or the arm. And we talked about, remember, we had Drew carrying around that motor, and we talked about when work was being done. Okay. So again, in this case, that object would be going with the field lines. So I lower potential energy. Okay. In this case, I am raising it up. I'm going against the field lines, and I'm going to increase its potential energy. I'm storing that energy in there. Again, the only thing new is thinking about it in terms of these gravitational field lines that we never drew in before. Yeah. So, similarly, when we talk about to move a charge in an electric field against its natural direction, okay, when we talk about natural direction, we're talking about field lines. Now, as a subnote, remember the field lines are always drawn how they're going to act on a positive test charge. So you have to keep that in mind. Okay. So the exertion of work by an external force would in turn add potential energy to the object. The natural direction of motion of an object is from a high energy to low energy. That's one of the main laws of thermodynamics. If you ever take any type of thermo or chem 2, you may have talked about it. Objects don't like to be high energy. They're always going to find a place to go from high to low. Okay. Must be done. And remember, that's a force times distance to move the object against nature. Okay. On the other hand, work would not be required to move an object from a high potential to low because that's what they want to do. Okay, so up here, this is talking about moving it against the field lines, and this is talking about moving it with the field lines. Okay. This would be analogous to an object, um, raising an object up. You had external work done by your hand, your arm. In this case, it's naturally falling. It's going with the field line. So that's like you just releasing the object, and gravity is doing the work. So in this diagram, when you go moving the positive test charge from location A to B. Again, I have a positive charge. That's what I want to identify. I see my field lines. If I go from A to B, I'm going against the field lines. A doesn't want to go to B. You're going to have to force it there. It's naturally want to go with the field lines. So if you moved it from A to B, you would be increasing its potential energy. It doesn't want to go that way. You're forcing it to go against those field lines. Okay. In this example, if you go from B to A, that's where it naturally wants to go. That's like dropping the object. You would be decreasing the potential energy. So this would be similar to like if you were going to lift that rock, and this would be like dropping the rock. Okay. Against the field line, with the field line. The field line is telling you where it wants to go, what it wants to do. In this case, my source of my charge is negative, so the field line is just the opposite. Okay. So in this case, if I'm going from A and trying to get it to go to B, okay, that's naturally where it wants to go. So in this case, you would be decreasing your potential energy. That's what it wants to do. That's like dropping it. In this case, if you go from B to A, it doesn't want to do that. You'd have to put some external force in there, external work. You would be increasing your potential energy. This would be like lifting. This would be like dropping the rock. Okay. With the field lines against, are you forcing it to do something it doesn't want to do? Or are you allowing it to go where it wants to go? Okay. And those are just all the verbiage on these slides. You can refer to them on the presentation of what we just talked about. With gravitational potential energy, we talked about that. Your formula you used over and over was mgh. Okay. Gravity 9.81 meters per second squared, but it was based off the mass of the object, and more importantly, we're tinkering with the height. Okay. So in these two cases, you got a 1 kilogram object at 2. If you just round it, I hate to round it, but just for our argument's sake, you'd have 10 joules of energy here, 20 joules here. More mass, more potential energy. You'd have 20 joules because you have 2 kilograms as opposed to 1 over here, 40. So you're at a higher potential, you're at a lower potential. You're at a lower potential, higher potential. Nothing new there. Now, we never talked about this because you don't really utilize it with gravitational potential energy, but we utilize it in electrical. So, what I want to do is kind of show you how we would have used it in gravitational and again make that link to electrical. Now, notice gravitational potential. We never talked about that. We always talked about gravitational potential energy. Gravitational potential energy is the amount of potential energy per kilogram. So in that last example, every time you change the mass of the object, you would have to redo the calculation, put another m value in times g times h. Now, when you're doing that with objects, typically you don't change the object. Electrical, a lot more different, a lot of moving charge, a lot smaller things, a lot more variables. So if you look at this, you're looking at the amount of energy, so the amount of joules per kilogram. So what that allows you to do is give you a ratio or something to apply it to any mass. So at this location, it would have 5 joules for every kilogram that you have. At this location, you would have 10 joules for every kilogram that the object is. So it's a more kind of generic, usable form. But notice the word gravitational potential. You drop the energy. So that tells you it's the ratio. Okay. So if you go back to that example, okay, yes, you had 10 joules, 20 joules if you use the MGH, that's your gravitational potential energy. But if I now look at the amount of potential gravitational potential or just potential that it has at this location on the ground, it would have 0 joules. I don't care how big it is. At this location, you have 10 joules for every kilogram, 20 joules for every kilogram. So in this case, you had 20 or 2 kilograms. So 20 joules per kilogram. If you had 2 kilograms, that's how you could apply this and get to the 40. Okay. And if you look at potential energy, it was MGH. Okay. So if I look at this gravitational potential, all I'm looking at is G times H. Is the gravitational potential. But again, the thing to think about is it's just a ratio of telling you how much potential energy for every kilogram that you have. At this location, no matter where you are at that height, that's how many joules you would have per kilogram. And then you just apply it based on how many kilograms you have. In this case, you had one. In this case, you had two. So it's just more of a kind of a generic ratio when you're talking about just the amount of potential, not potential energy, just potential. Okay. It is location dependent, as we just saw. At every location, it has its own amount. It is independent of the mass because it's a ratio. In gravitational, all it cares about is G and the actual height value. Okay? So it's describing the effects of gravity, a gravitational field upon objects that are placed at various locations within it. Again, it's the amount of joules per kilogram at that specific location. Okay? So now let's jump over to electrical. So again, comparing that. So like gravitational potential energy, electric potential energy is dependent on two types of quantities: the amount of charge, okay, and the distance you are away. And if you go back to our equations, that's what we talked about, the charge and r squared. So instead of it being the amount of potential energy per mass, it's the amount of potential energy per coulomb of charge that you're putting in it. Okay. So this is that electric potential. Notice it doesn't have potential energy, it's the electric potential. So that tells you it's a ratio, okay, of the amount of energy per coulomb of charge. It is independent of the charge right now. It is only dependent, okay, on that location and the strength of that field. So it is the amount of energy per charge. And remember, that's coulombs. So I'm dealing with joules per coulomb. So why do we use this? We use this as a way to express the effects of an electric field of a source in terms of its location within that electric field. It is a ratio. It gives us a lot more usability. It's a lot more user friendly. Has a lot more function and application. So in this case, this object here, this largest Van de Graaff generator, is creating a certain amount of electric field. Okay, so you'd have these field lines extending out. Let me get rid of this. And both these are at the same location. Okay. And so what they're going to do is you're going to be able to look at the electric potential. They would have the same amount of electric potential. And in this case, it would be 10 joules per coulomb of charge. This object has 1 coulomb, so it has 10 joules of energy, potential energy at that location. This object is twice as big, so it has 20 coulombs of, or 2 coulombs of charge, so it would have 20 joules of energy at that location. But its electric potential would be a 10 joule per coulomb charge, or sorry, potential. So you might be told that at this specific location you have 12 joules per coulomb of charge, okay, at this specific location with this specific field. Now, you can put any charge you want in that system and figure out how much potential energy that object has. So, for instance, if it was a 3 coulomb charge that you put at this location, it would have 36 joules of energy. If you put a 4 coulomb charge there, it would have 48 joules of potential energy at that location. So, it's just a much more user friendly. So, again, some kind of key takeaways. You have potential energy and you have this thing we just called potential. When you talk about potential, we're talking about a ratio. Okay. Whoops, sorry, ratio. And it's looking at how many joules of potential energy you have per coulomb of charge. Earlier, we talked about increasing or decreasing potential energy. Okay. And what you have to think about is with the field lines or against. If you're going with the field lines, you're going to decrease it. If you're going against it, you're going to increase it. Okay. This would be like lifting the object, and this would be like dropping your object if you compare it to gravitational field lines.